My name is Carolyn. I'm with the OSCAR, the Department of Energy Office of Science, and I'm the moderator for this next session. And I've read the abstracts for our next three speakers, and I think we have a good set ahead of us. They're going to take us from the smallest of the small with electronic structure theory to challenges in computational fluid dynamics, including the Rayleigh-Taylor instability and unsteady state. So up first, we have Aurora Pribram-Jones from the University of California, Irvine. Her thesis is in theoretical chemistry, and she studied under Kieran Burke. And her practicum was at Sandia National Lab in 2013. And I've learned that she is defending in August and is also a new mom. So with that, I will hand it over to Aurora.
Thank you. So today I'm going to talk about an idea that we have for new formalism that will allow us to eliminate the most expensive step computationally in simulations of warm dense matter. So first, this one. Perfect. The green dot. So first, I'll talk about what warm dense matter is and why we should care about it. So warm dense matter is a highly energetic phase that's intermediate between solids, liquids, plasmas, and gases, and it's got characteristics of all of those phases in one. You find it in the really high temperature and high pressure conditions that you'd find in planetary cores, the surface of the sun, neutron stars, or on the path to ignition of inertial confinement fusion. And the experimental facilities that you need in order to create those conditions are things like the National Ignition Facility at Lawrence Livermore National Lab, the Z machine at Sandia National Lab, where I did my practicum, the Advanced Light Source at Lawrence Berkeley, and the Omega Laser at Rochester University. What you do with these experimental facilities is usually probe the materials, unless you have something like the National Ignition Facility that has a very specific end goal. One thing that you can do with them is probe material properties at these conditions. And that's important for a variety of reasons. And for a theorist like myself, one of the reasons that it's important is because it can validate your theories. So what people have been trying to do is use experimental data like these things here, these at Lawrence Livermore in 2014. And this allows them to probe conditions that you'd find in planets. So up here you have Jupiter, you have Saturn here, and you can see that the data from NIF actually only begins to hit the conditions that you'd have in the Jovian core. So simulations are actually very important, and the reason that they're doing this comparison of different methods, theoretical methods in this paper, is because no method is so good at warm dense matter that we don't need to figure out new methods for doing it. And so we can talk about why that is by thinking about why they call this the malfunction junction. And the reason why is because in this phase diagram here, you can see that we have plasmas up in this area. So this is at very high temperature and at low densities. You have solids over here, low temperature, high density, and gases over here. Warm dense matter is intermediate to all of these things right in here. And you're going to find that when you're trying to access warm dense matter, that you're moving through things like taking a cold piece of metal and accelerating it into another piece of metal. You get very high temperatures and pressures, but that means that you're going to have to be able to model the solids as well in order to get the entire pathway into warm dense matter. So not only is it challenging within this phase itself because of its complexity, you also need to be able to handle other phases that are close by as well. So the way that you need to do that is have simulation methods that are both quantum and classical. Quantum effects are very important for the electrons because they're so dense that the electrons notice each other's neighbors still. But you have strong correlations between those electrons, sometimes between the ions as well, partial ionization, and a host of other physical characteristics that you need to be able to model. So if you have a model that doesn't deal with any of those single characteristics as well as the others, you're going to lose some of the material properties that you need to model well. In addition, the approximations that go into things like density functional theory, molecular dynamics affect the materials properties. So you need to be able to differentiate between the effects of the approximations and the effects of the models themselves. We can't avoid simulations, however, because as I showed on the last slide, you can't even access some of the conditions that you need for things like modeling planetary structure using experimental facilities. You also need that data for designing the experiments and for interpreting the data that comes out of them. You actually use these simulations to build equation of state databases that are important for interpreting the results. The other problem is that these experiments are super expensive. I mean, you can see with the flagship facilities that they're using that a single shot on one of those things is tons of money. So if we can find a way that we can replace those expensive and limited experiments with simulations that are not also expensive, then that would be great. So one way that people use simulations is through a method called quantum molecular dynamics. And the one that I'm used to and the one that I used in my practicum at Sandia was DFT molecular dynamics. So quantum molecular dynamics is a method that splits up the task of doing classical and quantum modeling at the same time. So for a given time step, you take a lattice of ionic centers, so maybe a chunk of aluminum, and you know where you think ideally those centers would be at 0 temperature. So you start with that guess, and you lay them down, and you say, okay, I'm going to use that as my potential for doing an electronic quantum mechanical calculation. Once you do that, you calculate the electrons using something called DFT, which you've heard about yesterday, density functional theory. And from that, you do a very, very, very big eigensystem solve. Normally, the eigensystem solve for density functional theory is expensive anyway, but at these temperatures, you're occupying a huge number of states. So you have this monumentally expensive calculation. And so once you do that, you have to iterate on that until you get self-consistency in the electronic step. Then you get forces from those electrons pushing on the ions, and that's going to move them to the next time step. Then you have to do that whole thing again for the next time step. So you end up getting these expanding calculations that get very, very expensive over meaningful time distances. So they're very popular because they work better than a lot of things for matching up with experiment, but they have a lot of fundamental problems. And these are the 4 areas that I've been working on in my PhD research and outside of it. There's no explicit temperature dependence in the electron calculations. They're computationally expensive, as I explained before. And in order to get response properties, like what happens to these materials when you hit them with a laser, which is an important thing for diagnostics and for experiments themselves, you need time-dependent electrons. That's not something that's naturally in this method. You get no energy transfer between the electrons and the ions because you're freezing the ions in one spot when you're doing the calculation of the electrons over that potential surface. So all 4 of these things are things I've talked about in my research, but I'm going to focus on the computationally expensive aspect right now. The way that we're going to look at this is by eliminating the DFT step in the quantum molecular dynamics that I talked about before. So this is a plot of that molecular dynamics step. So I'm going to start with some ion distribution, and then that's going to serve as the starting point for my quantum mechanical DFT step. This right here, the Kohn-Sham equation, solving these to get eigenvalues and eigenstates, is the computational bottleneck of these calculations. So if I could figure out a way to eliminate this yellow step, that would be paramount for reducing the cost of these simulations in general. One way that people look at doing that is with orbital-free methods, and that just means I have some direct expression for the energy in terms of the density. That works really, really well if you can come up with an accurate enough approximation here for the energy, and that's something that people have been working on for a very long time, and there has been progress made in that area, but what we propose is finding a way to get at energies that depend not on the density themselves, but on the potential. So if we zoom in on that electronic step, if we did things the way that I showed in the last slide, we would come over here to solving these Kohn-Sham equations, and we'd have to go through here until we were converged for every single time step. Instead, if we have some approximate density and some approximate functional for the energy that we're interested in, then we'd be able to bypass this entire step. Now, that only makes sense if coming through here and doing this self-consistent pathway here is less expensive than this one, and if we have approximate densities and approximate functionals both in terms of the potential. So potential functional theory is a way to get at that process. I'm going to relate it to density functional theory because I think it's much more likely that people are more familiar with density functional theory than potential functional theory. So density functional theory uses a clever trick to relate the non-interacting system of electrons with a certain density to the real-life interacting system of electrons with the same density that we actually care about. And it uses, the original density functional theory uses the Hohenberg-Kohn theorem, which is just that mapping saying that energy comes from densities. So I take some density and I have some functional that I put it into, a magical exact functional that nobody knows explicitly, and then out comes the ground state energy. However, the way that people are using this in practice in the vast majority of calculations now is through those Kohn-Sham equations, which says that this non-interacting system can be mapped onto the interacting one. Instead, we can use potential functional theory to take a potential and put that into a different functional, and then the output of that will be the same ground state energy. This DFT mapping is exact in theory, and so is this potential functional mapping. What my collaborator and I have done is we've extended this to finite temperature. So we've created a new functional that has temperature dependence in it and gives us the finite temperature energy, a free energy, which is what we're actually interested in. One of the key ideas here is that we're going to piggyback on the cone-sham system without solving those cone-sham equations. So the people who are running these simulations are very, very familiar with this large history of density functional approximations for interaction pieces of the energy. Those are the things that don't have explicit temperature dependence in them right now, but that a lot of us are working toward building approximations for. However, we can use their knowledge if we take a finite temperature potential functional theory and input something for the rest of the energy. So not the interaction part, but the kinetic energy and the entropic energy that comes from a non-interacting system of electrons. So my main contribution here has been in developing the formalism. And so this is the major result that we have that allows us to make a key difference between the way normal orbital-free methods and density functional theory work. So what we can do is take this entropy, which is the universal part of the free energy of a non-interacting system of electrons. So these are the things that don't really depend on where those electrons are sitting. Like electrons sitting next to each other have a certain kind of interaction, whether they're in a deep pit or in a shallow bowl. So that's this energy here, and we have written it in terms of the potential, and the way that we've done that introduces no additional error on top of a density functional in terms of the potential. So what that means is all I have to construct is an approximation for the non-interacting density in terms of the potential, and I get if this is highly accurate, I will get a highly accurate energy out with no additional error added on top of that. We do this by going through something called the coupling constant, which is like a dial connecting that non-interacting system to the interacting system. So that coupling constant is used in something called the adiabatic connection, if you're familiar with that, or in thermodynamic integration. What that does is it lets you do an average over the expression of the density in terms of the potential over that coupling constant, and through that we're able to get this corresponding approximation to the free energy that is corresponding to a specific approximation of the density. So what we did is we came up with that formalism, and then we tried to figure out a way to demonstrate that it works well before we went on to the larger task of doing it for large systems, three-dimensional, and implementing it in larger codes. So our numerical demonstration is a simple system that we can solve exactly and really peel apart like an onion and get to the nitty-gritty about what works and what doesn't. So if you take a box with infinite walls and put some bumps at the bottom, and then you drop 5 electrons into it, at zero temperature, you would get this gray background here. And you see that you have big quantum oscillations here from where there's a high electron density. If we heat that up to worm-dense matter conditions, it's going to go to the black line here, which is much smoother, but not completely smooth. You still have some quantum oscillations, which are important. And you can see that our approximation, the red line, this potential functional approximation, lies right on top of that. That high accuracy comes from using an asymptotic approximation known as a semiclassical approximation, which really is the fundamental underlying mathematical physics underneath why density functional theory works so well for such a low cost. So we took that idea and we applied it instead of to density functional theory to a non-interacting density approximation. So once we have that, we can compare it to things that are computationally comparable in expense, something like Thomas-Fermi. Thomas-Fermi is really, really smooth, doesn't get the boundary conditions correct, but it's fast. So it's a quick and dirty sort of thing to do at these temperatures. If you increase the temperature to have hot dense matter or plasmas, Thomas-Fermi works really, really well. But you can see that at these intermediate temperatures where the density is still important, it's not going to work quite as well. So for us, the key is that for the same cost as this curve here, we get the really accurate density approximation that we get there. Now, if our system works properly, we'll be able to take this very accurate density approximation and put it into our formalism and get out a very, very accurate free energy approximation without it introducing any additional errors. So the way that we looked at that first was looking at an energy density. Now, energy densities don't really tell you, they can be tricky, so you have to be careful when you look at them. But one thing they can tell you is that if you have errors down here, so we can see that if we compare Thomas-Fermi, this green curve, to the exact black curve, that it doesn't do that well down here near the edge regions or in the center. However, these errors balance out when you integrate to get the entire free energy that you're actually interested in. And so you actually get a much better answer than you'd expect, but for the wrong reason. And I hate getting the right answer for the wrong reason. So I like looking at this here and seeing that our potential functional approximation, when plugged into our coupling constant entropy formalism, gives us a really nice approximation, which is this red line lying right on top of the black line all throughout the entire region, despite having different asymptotic regions in this simple example. If we integrate that, we're going to get the energies that we actually care about for those simulations. And you can see that we can look at, if we look at this lambda here, this lambda is a parameter that we use to express how close we are to the warm-dense matter regime. It's a ratio of temperature and chemical potential, or Fermi energy, depending on how you talk about those things. And it lets you find where you're going to have comparable influence from kinetic energy and potential energy. And so if you look at around 1, that's where we'd be in the warm-dense matter regime. This far right column is our potential functional approximation. And this is, by the way, if you look at the scale here, this is 100 times the actual error in our method. And you can see that it does much better than Thomas-Fermi or something called the Kirchnitz, the gradient expansion approximation with the next order put in there, which is like doing a Taylor expansion and comparing it to an asymptotic expansion. So here you can see that we're doing a really good job being accurate across whole regimes between condensed matter, very cold, and hot matter, and still getting the warm dense matter right in the middle. So future work, I'll be doing at Lawrence Livermore in my fellowship there, and this is one track of that proposal, and I'll be working on testing different classes of potentials and hopefully extending it to 3D systems and implementing it into a potential functional theory molecular dynamics code and comparing it to VASP using their high-performance computing facilities there. So in summary, I've come up with an orbital-free, therefore computationally efficient code for one dimension that takes advantage of decades of DFT research, utilizes the unreasonable accuracy of asymptotic expansions, and connects disparate regions of phase space from condensed matter all the way to plasma. I'd like to thank my advisor, Kieran Burke, my collaborator on this project, Attila Changi, all of my other collaborators, UCI Chemistry in my group, and also, of course, Krell and the CSGF, because without them I wouldn't have had the freedom to do an independent project like this. Thank you.